Hello Chem 1B, this is our solutions chapter video 9, and we're going to be talking about osmotic pressure of solutions in this video. Now in order to talk about osmotic pressure, we need to talk about osmosis. As you may guess, they are related to one another. So when we think about osmosis, the primary thing we're going to be thinking about is a semi-permeable membrane. Because in osmosis, what's happening is there is solvent flow from one side of a membrane to another side. Now, what is a semi-permeable membrane? A semi-permeable membrane is a thin layer of material that will allow only small things to pass through it, like molecules. Now, depending on the membrane you're using, you may be able to change what's known as the pore size of the material, which will allow different size of molecules through, while keeping others on one side of the material. Now, this has a lot of applications in biology, for sure. Animal kidneys, cell membranes, these are all examples of semi-permeable membranes. A big aspect of osmosis occurs in purification of water, where we use osmotic filters to purify our water. Now, if we kind of look at this picture on the right here, my gray thing that I have right here is my semi-permeable membrane. And you can kind of see there's holes in it that is allowing our water molecules to move through the membrane. But then let's look at some of these other things on the left side of our membrane, because on the right side, it's all just water molecules. On the left side, there's some stuff over there. Now, the first thing that we can kind of probably rule out is hopefully we can all see that this big clunky molecule here is probably not going to fit through our little hole that we have in that membrane, so it's stuck on the left side. And so this is an example of where the water molecules are allowed to pass through, but our large molecules, they're definitely not passing through that tiny little hole, and so they're going to get stuck on the left side of the system. Now, at the same time, we have these ions present. Now, it kind of looks like the ion might be able to fit through that hole, but there's a problem. And something we learned in Chem 1A is something of an intermolecular force called ion dipole. And in ion dipole, what happens is a polar molecule is attached to an ion. And water is definitely a polar molecule. It has a partial positive charge on the hydrogens in its substance and a partial negative charge on the oxygen. And so if we look at these water molecules around this negatively charged ion up here, you might notice that all the hydrogens are facing that ion. This is because they're all attached to that ion in an ion dipole interaction. The positive water ion, if you look at it, all the water molecules surrounding it have their oxygens facing the positive charge. Well, this is because the partial negative charge on water is on oxygen. And so they're all attached via these ion dipoles. Now, if we look at the blue circles, they're way too big to pass through our hole in our membrane. And so all the ions in the blue and white clunky molecule, they're all stuck on the left side of our semi-permeable membrane. Now, another thing that we should be able to identify is which direction are those water molecules moving? Are they going from the left to the right or the right to the left through our membrane? Because they are definitely moving, and osmosis is all about that movement. So the definition of osmosis is that solvent will flow through a semi-permeable membrane from the more dilute side of the membrane to the more concentrated side in terms of solute concentration. Now, because there is 0 particles other than water on the right side of our little image here, and then there's all this stuff on the left side, water is going to flow from the right because there's less concentration of solute particles present to the right side where there's more present. We can see that occur in like a fun experiment that you could do at home right now if you have vinegar and eggs. So what we can do is if we remove the eggshell from an egg without breaking the egg itself, which is kind of hard to do. You can't like hit it this way. What you need to do is you need to dissolve the eggshell. And we can do that by putting the egg in vinegar. Vinegar will react with the eggshell and remove it for us. If we leave it in there long enough, our egg will become shellless. Then what we can do is we can put the egg
in two different solutions. One in a pure water solution, right here, and two in a concentrated sugar solution. So basically all we do is we put a bunch of sugar in water and dissolve it at a really high concentration. And what you'll see happen to our shell-less egg is that in the pure water solution, our egg gets way bigger, right? This is the size of it here. You can see that it got much bigger in the pure water solution. Whereas when we put the egg in the concentrated sugar solution, you see that it got much smaller. It's pretty neat to watch. The reason why is because of the flow of osmosis, right? In this solution, water flows into the egg, making it expand. In this solution, water flows out of the egg, making it shrivel. And this is all due to a concentration difference. In the pure water solution, the concentration is higher inside the egg than it is outside the egg of solute. And so water flows into the egg. But in the concentrated sugar solution, we have such a high concentration of sugar outside the egg that water is going to flow out of the egg to try to dilute our sugar solution. Now, this guy here stops getting bigger. It can't continue to get bigger. And the reason why is because as more and more liquid flows into the egg, the membrane expands and the pressure inside of the membrane increases. Eventually, the pressure inside of the egg gets so high that we can't get osmosis to happen anymore. This is what's defined as osmotic pressure, the pressure at which osmosis will stop occurring, or the pressure that is required to stop osmosis from happening. So let's look at an equation for that. So again, osmotic pressure is defined as the pressure that must be applied in order to stop osmosis from occurring. Osmotic pressure has this equation where the uppercase pi symbol is our osmotic pressure, I is our Van't Hoff factor, M is our molarity of the solution, R is the ideal gas constant. This one is the 0.08206 atms liters over moles Kelvin value, and T is our temperature in Kelvin. This equation will be given on the test. You don't need to memorize it, but you do need to know how to use it. Osmotic pressure can be measured a bunch of different ways. Now we have machines that can do it for us, or instruments that can do it for us digitally, not manually. But one way to do it is to put a solution inside a semi-permeable bag and attach that bag to a glass tube like so. Now, this is kind of a snapshot. Once osmosis starts occurring here, water's going to flow into the bag. That's going to cause this liquid to rise up the glass tube. If we measure the difference in height from where the water went versus the height of the water in the beaker, we can calculate the osmotic pressure. We also need to know the pressure in the room. We're not going to do this. We're going to use the equation, but this is how you could measure it in a lab setting. So let's do a calculation. We want to know what the osmotic pressure of an isotonic solution of 0.155 molar, and it's a saline solution, so that means NaCl, at 37 degrees Celsius is. We know that the osmotic pressure equation looks like that. We know that the ideal I value for NaCl is 2. We're going to assume 2 because in the problem here it didn't tell us what the real value of I was. If I told you that the real value is 1.8, then you should use 1.8. But since we don't know what it is, it wasn't given in the problem, we'll just use 2. So our ideal value, or our osmotic pressure here, will be equal to 2 times 0.155 molar times 0.08206 atms times liters over moles times Kelvin times our temperature in Kelvin, which is 310 Kelvin. So if we multiply all that out, we get a pressure of 7.89 atms for our osmotic pressure here. And this is an example of using the equation. Okay, we have one last topic to cover in Chem 1A entirely. Congratulations.